Okay. You can introduce yourself and you can start.
Okay, just to confirm, can you see my screen and my pointer here?
Yes.
Okay, okay. So my name is Leonardo Oliveira. I'm here to present this paper. I am a master student in the Federal University of Juiz de Fora, Brazil. The paper is entitled NWDAF Study Employing Machine Learning Models on a Simulated 5G Network Dataset. So this is the content of my presentation. I'll begin with the introduction. So this graph here shows the main characteristics of each telecommunication generation. And if we take 5G here as an example, it's expected that it could achieve up to 100 times of the speed of 4G, and it could reach up to 4 gigabits per second of peak download speeds. And this generation comes as an enabler for the Internet of Things, smart cities, autonomous car, and remote robotics contexts. And if we compare 5G with the previous generations, the main point was the introduction of the so-called service-oriented or service-based paradigm. This enabled the possibility of virtualization a lot of elements of the network. And this virtualization improved the level of flexibility, and this helped in the deployments of the network and in the experimentation too. So the 3GPP, which is the third generation partnership program, contains the working groups that specify how the technology of mobile communication works. And their specifications are called release. For this work here, the main ones are release 15 and the release 17. Release 15 contains the specification of what we call 5G nowadays, and it is the 50th generation of cellular mobile communications. And in release 17, the network data analytics function, or NWDAF, was introduced with a greater level of detail. And besides the NWDAF description that I brought a reference here, we had the introduction of the interaction or signaling between the NWDAF and other network functions via the service-based interface APIs. And the reference is here for this part. So a little bit of background. This graph here shows a 5G core overview. Each of these gray boxes here represent the so-called network functions, and each network function implements a functionality in the 5G network in a way that they work together in a cohesive way to provide the services. And if we highlight the upper part of this image here and zoom it in, we see that the NWDAF was expected to be introduced since the inception of the 50th generation. I will dive into the details of this function during the coming slides. But before that, I will present to you a non-exhaustive list based on the specification of the 3GPP, the reference here, of the use cases involved with this NF, the NWDAF. So it could help the operator calculate the slice load. User equipment behavior prediction is related to the NWDAF2. And the other use case related to information, so information regarding the network function load, the network general performance, UE mobility, and UE anomalous behavior. And our focus on this work was the communication information. The specification treats this as UE communication information use case. So the NWDAF is highlighted in orange here. So when we implement it, given the details of the release 17, we can implement two logical functions, split its functionality in two logical functions, the ANLF and MTLF that I will detail now. So the first one is the analytics logical function, ANLF, and it is responsible for receiving analytical data in this flow here that I will explore later. And it can make requests of inference for the MTLF if MTLF is implemented, and if not, the ANLF makes the inference by itself. And its main objective is to provide the analytics service, so the so-called analytics service exposure in the specifications. The MTLF, which stands for Model Training Logical Function, is responsible for the model training itself, and it deploys the trained or pre-trained model. So this is the training service exposure according to 3GPP. So coming back to the graph here, we see that in release 17, we have the presence of the analytical data repository function, ADRF. Then this function connects to the other functions I previously mentioned to you in the 5G core and obtains the data. Then there is this feed is established, so the NWDAF can receive the analytical data. And then ANLF can request a prediction, for example, and the MTLF connects to a model manager. This model manager receives the commands and the feedback from the MTLF, and it deploys the model for the MTLF. It's possible to implement the model manager within the MTLF in the 5G core, or we can do it in a cloud external environment, which is the example we brought here. And the model manager can contact a database, in our case here, a data warehouse, to store the trained model. On the other side here, the ADRF can generate the historical data, storing this data in a database. But before it does that, the data goes through a ETL process, so the extracted data, cleaned, etc., is stored in the database. Okay, so now the results of the work. As initial contributions, we run a validation of the work by Kim and others, and during this task, we could improve the supporting documentation of this work, and we could update their implementation to work correctly on the Free 5GC 3.3.0, which was the stable version of this core at the time. And we come up with a testing environment. We used HunSim to simulate the pair of we and the Han in our environment, and this was connected to a 5G core, which is the Free 5GC I just told you, and we implemented 3 other services to connect to the we. So the first one was the ping host, so it could reply the ping requests from the we. The second one was a video server, so the we could play multimedia. And the third one was a web server that contained web pages, so that we could simulate web browsing. Each one of those services here represents a different set of requirements for the quality of service or quality of experience of the user. So we created a data set using the T-Shark utility that sometimes is called the Wireshark-Li, and each capture contained exactly 1,000 packets. And we had access to 7 different features because the data was recorded in a PCAP format. So this PCAP format gave to us a counter, integer, counting the number of packets captured, the time, which is the relative time from the beginning of the capture and the capture of a given packet, the source and destination IPs, a protocol label tag that is given automatically by Wireshark itself, and length in bytes of each package. And the last one is info, which is the extra information captured during the experiment, but that didn't fit any of the other features. So we ran a preliminary data analysis in the data set, and we could, and first we analyzed the packet length distribution. So this graph here shows this distribution. And if we take, for example, the ping activity, then there is a concentration in 84 bytes of packet length, because the Linux system that we run in the UE, virtual UE, contained a 60 byte payload length, and that was added to 24 bytes of the reader of the packets. The other packets that are here are variations of this payload size. The video contained this, had this behavior here, and the distribution was concentrated here in 1,452 bytes of length. And this probably happened because as we was playing a video file that contained like a dozen megabytes of size, the large file was splitting packets, so it generated this behavior here. The other packets here probably were the metadata packets and the control for play, pause, the media, etc. And last, the web, if we analyze this distribution of the packet length here, we see that in the web case, there was more evenly distribution in the length. And this probably happened because as the we was browsing the pages, the objects of the pages were split in different packets. So there is this behavior here. Okay, so in this preliminary analysis, we wanted to know the frequency of occurrence for the protocol tags given by Wireshark. So if we take ping as an example here, we see a massive presence of ICMP, and on the other hand, on video and web, the presence is massive on TCP and HTTP on the second place, and this packet here is the metadata packet of the file being played. We run some machine learning models on this data set, the decision tree, multi-layer perceptron, and random forest. The results for the classification problem are in this table here. So the best one was the random forest with almost 76% of accuracy. The second one was the decision tree with 74, and the multi-layer perceptor was the third one. And we wanted to know the feature importance given for the models. So the weight for the random forest and decision tree models was concentrated in the protocol feature. In the second place, we have the length feature with 28% score here in the random forest. But that was the feature importance distribution. So in the next picture here, we have a confusion matrix for the random forest. Due to the design decisions we made during the project, this result would converge in the other models too. So if we take, for example, the ping here, it was possible to see that it achieved 100% of accuracy, but on the other hand, the video and web had around 60%. So if we come back to the results I just shared with you, it's possible to infer that this behavior here of the matrix could be explained because the ping was easier to differentiate, as we see in this figure here, and the models gave more importance to the protocol. So probably this could explain these results in the matrix. So coming to the conclusion, future work, the conclusion, it was possible to build upon the work of Kim and others, as I told you, and it was possible to run a study on the NWDAF in a computer networks context because Kim and others didn't do it. And we made a reproducibility-wise implementation because we have a publicly available source code. The URL will be shared in the end of this presentation. We could make a supporting documentation for our work too. And we made design decisions that prioritize the repeatability of our work. It was possible to create a 5G data set on a simulated testing environment. And we could run experiments on the UA communication information use case specified by 3GPP. As future work, we want to finish the integration of the current NWDAF implementation we made with the free 5GC, and we want to explore other data preprocessing techniques and machine learning models to enhance the accuracy of our predictions, our classifications, and we want to explore network traffic generation models or to describe the traffic patterns we already have in our data set or to create others to enhance the repeatability of our tasks. And we want to explore other testing environments and apps and with other applications running on this environment to create, for example, concurrent traffic on the environment. We want to experiment with real WEs because currently, as I told you, we are using simulated ones, and all the tasks will end in developing a NWDAF open source experimentation framework that we would love to share with the community. I need to acknowledge the lab I'm part of in the university, and I need to acknowledge the Federal University of Juiz de Fora and the CAPES institution for funding this research. These are the references I used in this presentation, and that's it. This QR code gives you a copy of this URL that contains the source code and the data set. Thanks for the attention.
Thank you. there are some questions from the audience.
Okay.